Okay, so here's where we were last time. We were talking about what it means for a function to be bijective. Right, so the big idea of bijective is that there's a sort of a perfect pairing. Bijective means perfect pairing. If you have a domain here, target there, points in the domain, points in the target, right? Perfect pairing, like so, for example. And to be precise, for every point in the output, for every target, there needs to be exactly one preimage point. So for every point in the target, exactly one preimage. Exactly one preimage. So at least one point in the preimage means that it's onto. At most one point in the preimage means that it's what they call one-to-one, which is an unfortunate choice of terms. All we're interested in, though, is what it means to be bijective, and there is, again, the idea of bijective is just a perfect pairing between the points in the domain, points in the target. All right, so the assertion that's made in this corollary is that if you have a linear transformation that's bijective, that the dimension of the domain is equal to the dimension of the target. Okay. Now, the way we prove that is actually an immediate consequence of this theorem right here. And let's just apply the idea. So suppose we have, V is over here. There's V. And we've got W here. And let's draw our scenario. By the way, we need to make note of where the zero vector is. Right? Well, our function looking something like this, for example, our function being bijective, what is the kernel of such a function? Well, the kernel, what's the preimage of 0? Well, 0 is a single vector. There is therefore a single point in its preimage, that is the 0 vector. So this kernel consists of only the 0 vector. Just the 0 vector. And the dimension of a single point, right? It's not one-dimensional. One-dimensional would be like a whole line. A single point is what we call zero-dimensional. So in this case, that number is 0. Okay. Now, next question, what can we say about the image? What is the image in this situation? Well, the image is a collection of all outputs. Well, every point in the target has a preimage, therefore every point in the target is in the image. And therefore the image is exactly W. The image is the target. Right, so in this case of a bijective linear transformation, that term is 0 and thus goes away, and therefore our result is dimension of V equals dimension of W, as we were alleging down here. Bijective linear transformation, domain and target have the same dimension. Okay, so this is a nice theorem, and it turns out this is exactly what we're going to need to be able to prove an old result. Today's a day, by the way, where we're going to be proving a bunch of old results that we kind of waved our hands at back in chapter 4. So specifically this one, you may recall that we made the assertion, if you're looking at a homogeneous differential equation, constant coefficient. Well, we don't even need constant coefficient. Homogeneous differential equation, linear, nth order, satisfying the conditions of the existence and uniqueness theorem. The theorem said that the set of solutions is a vector space. We already proved that. And what we have not yet proved is that it's an n-dimensional vector space. Now, we did a lot with this. We capitalized, we profited immensely on the idea that the set of solutions was n-dimensional. Knowing that the set of solutions was n-dimensional was how we could conclude that the n solutions that we found are all of them, right? Or, a basis, a fundamental set of solutions. So it required making a dimension argument, and that dimension argument requires knowing what the dimension is. So this was a key fact in chapter 4 that we never proved. Now, I did make a vague reference to the proof being in the book, and if you want to read the book's proof, you're very welcome to. I don't care for the book's proof. It's extremely clunky. It's very hairy. It's got a lot of details in it. It's like 2 pages long. Oh my gosh. And ultimately what they're doing is kind of setting up in gory detail what we're going to cover at a very high, convenient level in this argument, right? That I think, again, is much nicer. So I'm going to show you this proof, and then if you'd like to take a look back at the book's proof and compare and contrast, I think you'll find what I'm about to show you here a much more convenient argument. So here it is. I'm going to define a couple of vector spaces. Bear with me. This thing that we're trying to understand, the set of solutions, we already know that's a vector space. Proved that back in chapter 4. Next vector space I want to talk about, the collection of initial values, or you might call them initial conditions. And recall that when you're looking at a differential equation, there's a bunch of solutions, but if you set initial values or an initial condition, right, that consisting of the value of the function you're looking for, the value of the derivative, all at a, et cetera, all at a single value of x. We call that an initial condition. And we didn't use the following point of view in chapter 4, but if you think about it, a collection of values of the function and various derivatives, it's just an ordered list of real numbers. There are n of these real numbers that make up an initial condition, and therefore an initial condition is an ordered n-tuple of numbers. An initial condition is a vector in Rn, if you choose to look at it that way, which I would like to do. Okay, so another vector space, as it turns out. All right, and with those vector spaces being defined, I would like to now make an important new object, and that is a linear transformation from the set of solutions vector space to the set of initial conditions vector space. This new linear transformation that I'm defining is defined by the following formula, and ultimately a very easy formula. If you give me a solution, color coding, if you give me a solution to the differential equation, compute the corresponding initial values. Right? If you give me a function, you can plug in x equals 0. You can take various derivatives into which you plug in x equals 0. You can assemble those into the initial condition that produced that solution. Okay. Real easy little formula there. Okay. Now, I claim that this is a linear transformation. How do I know this is a linear transformation? Well, it's a plug and chug direct confirmation. Let me remind you, we did a bunch of these last time. Right? So, for example, this Dirac transformation here, the act of plugging in x equals 0 turns a function into a real number by what is, in fact, a linear transformation. A direct check. The way you check is just like the way you check that the derivative, that differentiation is a linear transformation. Just put a linear combination in, confirm that you get the expected linear combination out. So it's a straight up plug and chug. And I would like for you all to take the time to do this. Confirm for yourselves that this function from S to I is a linear transformation. Okay, exercise for you all to do on your own. Highly plausible, I think. Okay, well, it turns out that we're like a hop, skip, and a jump away from being done with this proof. All we've done is make a couple of observations. Observe S that I'm trying to understand as a vector space. The initial conditions are a vector space. And all I've got to do now is, like I say, a couple of quick observations. And they are that this linear transformation T is 1-to-1 and onto. In other words, this T is a bijection. It's a perfect pairing. And why this is a perfect pairing is just a reference to another old fact, something that we've known for a long time. It's the existence and uniqueness theorem. Let's talk about the existence and uniqueness theorem for a moment. temporarily, let's set aside all this chapter 5 stuff that we're doing. Just flash back to chapter 4. In chapter 4, the existence and uniqueness theorem says that, okay, certain conditions have to be checked, but if you give me an initial condition, there is exactly one corresponding solution. Right? That was the big result. For every initial condition, there's exactly one corresponding solution. None of this, contradictory, seemingly multiple solutions, not funny business. There won't be any situation where somehow you just can't get a solution. Initial condition, exactly one corresponding solution. Okay. Well, in this context, let's think about what that means. For every initial condition, okay, so for every point in the target, there is a corresponding solution. Therefore, there is exactly one corresponding point in the domain. For every initial condition, there's exactly one solution. For every target point, there is exactly one domain pre-image. And that's exactly what it means for this function to be a bijection. Right? Always exactly one pre-image. Okay, so we have here then a bijective linear transformation. This theorem says that a bijective linear transformation has this property. The domain and the target have the same dimension, and we are basically done here. Let's look at our situation again. Our domain S, this is the thing whose dimension we want to understand. Our target I is Rn. I understand Rn very, very well. Right? Rn is clearly n-dimensional. So if the dimension of my target is n, the dimension of my domain is n. And therefore, the vector space of solutions to my differential equation is n-dimensional, as I wanted to show. Right. Oh, I'm sorry. There we go. Yeah. So, really nice result. Ultimately, there's a couple of details to check, and I've left it as an exercise for y'all to confirm that this is a linear transformation. And yes, you do have to understand what the existence and uniqueness theorem says, right? But with those established, this is a short couple of steps to prove this result about the dimension of the set of solutions. And I want you all to compare that to what you see in the book when you go back and look at chapter 4, section 4.1, when they finally, when they get around to proving this result, and it's a hairy mess of ugly details that is very rigorous, perfectly rigorous, but ultimately very opaque and unsatisfying. So I like this one a lot better. Hope you might as well. Anyway, you're certainly you can look at either one that you like. Okay. All right. We're then going to move on to section 5.2. Linear transformations we've already talked about. I'm going to give you a different point of view on linear transformations in this section. We're going to try to reinterpret linear transformations as elemental objects. So, right now, the idea you have in your mind, and this is perfectly appropriate, what is a linear transformation is that it's a function. It's a function that has a certain nice property of linearity. It's good. Okay. So, let's think of it differently as being a thing, an elemental thing. And that I might have multiple of these elemental things. And I might, for example, want to add these elemental things. And I might want to, perhaps multiply one of these by a scalar, or maybe I want to take these elemental things and multiply them by each other. Let's think of them as elemental things and try to develop an algebra of those elemental things. Now you might be thinking, what a weird thing to do, why would anyone ever do that? Let me remind you, we already have done something kind of like this with matrices. Right? Didn't seem that weird at the time, but matrices started off being a shorthand to represent a linear to represent a system of equations. Chapter 1, right? We've got a system of equations, got a bunch of stuff we did with systems of equations, and a matrix just was a shorthand representing that. We thought of them as, in a, I'm going to say, a complicated kind of way. And then in section 1.2, we said, okay, yeah, sure, but let's also think of them as individual elemental objects that I could add, and that I could multiply, and then I could multiply by scale. We set up an algebra of matrices, even though that's not how we originally thought about matrices. We're in exactly the same situation here. Right? So, seemingly a little weird at a glance, but ultimately, you gotta admit, we've been down this road before, kind of, so not that weird, really. Okay, so let's flesh this out. Here's how we're going to define what it means to add two linear transformations. Here's how we're going to define what it means to multiply a linear transformation by a scalar. Let me point out that both of these are recycled definitions. After all, linear transformations are functions. And back in chapter 2, we defined what it should mean to add two functions when we were defining vector spaces of functions. Right, so in section 2.1, we defined what it should mean to add two functions. Well, this is exactly that definition. And we defined what it should mean to multiply a function by a scalar. This is exactly that definition. So none of this is really new. I will point out one thing just to be clear. These operations, well, let's talk about that one, for example. This operation of addition, that is the addition operation inside of W. After all, T of B, S of B. Those are outputs from T. Those are elements of the target. And so what does it mean to add two elements from a vector space W? Well, it means whatever add means in W. So this is an existing vector space operation. On the other hand, this, unfortunately, written with the same exact symbol, is not just automatically to be assumed to be, the vector space operation. This is the operation that we are defining, right? Over here on the right-hand side, we are adding elements of W. Over here on the left, we are adding functions, right? So we define the left addition by capitalizing on the existence of the right addition. But they are not the same operation. They're just closely connected in this way. Okay. Alrighty. So likewise with scalar multiplication, what does it mean to multiply k times a scalar? Well, that is whatever W says it means. And with that operation in W, from that we can then define what k times a linear transformation ought to be. This scalar multiplication is a ripoff of that scalar multiplication that already exists. Okay. All right. Now here's the bad news. If I want to define a multiplication, I can't do this same trick. I can't say t times s. Well, we'll just rip off. We'll just multiply the output values. Now let's just take the vector multiplication in W and steal it, just like we did here. The reason we can't rip off the vector multiplication in W is because there is no vector multiplication in W, right? W is a vector space. There's an addition operation. There's a scalar vector multiplication. There is no vector multiplication. So we're going to have to deal with that differently. We make a different definition of multiplication. It's done as follows. We're going to define a product of linear transformations by composition. And I'm going to give you two, I think, really persuasive reasons of why. The first one is because this is what the rest of the mathematical community does. This is the standard definition to make, so that's a good reason. Let's get on board with what everyone else is doing. But a more persuasive reason is that, as we will see in a moment, this choice, and I emphasize it's a choice, it's a definition. Definitions are choices. If we choose to define a multiplication of linear transformations with compositions, we will find ourselves looking at an algebra that's very familiar, that has a lot of nice properties, and in which we can do a lot of things, and we're going to end up being able to prove some big theorems with this choice. Right? So you're going to see that play out over the rest of this lecture. I just wanted to mention that here because it does seem arbitrary. It is arbitrary, right? Kind of pulling it out of thin air. And anyway, you'll notice all the wonderful things that we're going to do with this choice, but I just wanted you to have that thought heads up in advance. Okay, so y'all know what composition means. Composition means that whatever you're putting in to the composition, well, that thing goes first into whichever one is on the right. Whichever one is on the right. And then after it goes into that one on the right, then that output value goes into whichever one is on the left. It's a succession of plugins. Same composition you've seen in other contexts. Okay. All right. Now, I do have to point out one really tragic thing about this definition. It's very unfortunate. And I have a personal story on that. I'll tell you in a minute. But notice that the notation appears to be backwards. It does look kind of backwards, doesn't it? I mean, so for example, look, the first linear transformation to act is T. That acts first. And then whatever comes out of T then goes in to S. And S is the one that happens second. Right, so T is on the left, S is on the right. That's how we do things, right? The left to right. And yet, unfortunately, when you compose functions, the one that acts first is on the right, and the one that acts second is on the left. As it kind of has to be, because look, I mean, the one that's sitting next to the V has got to be the one that acts first. And the one sitting next to the V has to be the one on the right. So this is just kind of how it has to be. There's no really feasible way around this notational tragedy. All right? So what I'm going to tell you all is heads up. Do be really, really careful about this. When you are writing a product of linear transformations, think through very carefully that you're going to have a seeming discrepancy with which one is on the left, which one is on the right, whether you're writing it in algebraic notation or whether you're writing out like a diagram, thinking of order of events. It's just, like I say, it just is what it is. So the personal story, when I was in graduate school, one of the research problems that I was working on involved certain kinds of functions. They were not linear transformations, but there were certain kinds of functions that were being composed, and that those compositions were being interpreted as products in a kind of analogous to this, but in a very different way. But in graduate school, in case you don't already know this, problems that you work are not problems that take, somewhere between 5 and 20 minutes, right? Like a Math 216 problem, it was a really hard homework problem. It took me like 30 minutes, right? In graduate school, problems that you work on might take months or years, right? So this particular problem that I was working on was a very significant, hard problem. And I found, after being a month into the work, that I had made this mistake. I got them backwards, and in the diagram, the one that was on the left, and I wrote it on the left in the algebra, which is the backwards, right? So I had made exactly this mistake that I'm warning you about here, way back at the beginning of that calculation. So I had a month's worth of calculations that I had to pick up and drop into the trash can. Right? Because of this sneaky little, nasty little notational, that's why I call it a notational landmine, right? It can really mess you up. The way I like to say it, I don't make this mistake anymore. Right? I'm really good. I am always highly attentive when I'm thinking about compositions and which one's on the left and which one's on the right. School of Hard Knocks and all that. So I hope y'all will learn from my painful experience, right? And be ultra careful and always think through which one's on the left, which one's on the right. So, for your consideration. Alrighty. So, we've got an addition, we've got a scalar vector multiplication, we've got a vector product, and with all of this together, we have an algebra. And look at all these properties. Isn't this nice? Right? So, seemingly an arbitrary choice on the definition of what it means to multiply, but man, those choices that we made behave just like good old high school algebra in a lot of really convenient ways. And it's going to turn out that being able to use these properties is going to be a necessary part of being able to use this new tool, this new algebra, to prove some big results that we'll see coming over the rest of this lecture. Okay, I suggest that you prove a couple of these on your own. I'm going to show you how to prove this one. All the rest of the proofs, all the remaining 8, are highly analogous. Right, so watch how I do this one, and then just to make sure that you've got it and that you really do understand, pick another 2 of these, for example. Make sure that you can do them on your own. Right? I don't think it's worth your time to prove all of them. That seems a little overkill. If you're good with 2 of them, feel like you understand how that works, that's fine. Okay, so here's that proof. Oh, I got a little ahead of myself. Do notice, conspicuously absent from that list is commutativity of multiplication. Right? This is disappointing. And high school algebra, A times B is equal to B times A. In the algebra of linear transformations, you don't have that good fortune. So multiplication is not commutative. Yeah. It's too bad. And yet, not exactly the first time we've faced this, right? Matrix multiplication is not commutative either. So let's not throw out the entire operation just because of one minor previously experienced disappointment. This is not that bad. Nevertheless, heads up. Okay, so we're going to prove this fact. Here we go. This is the proof. I want to prove that this is equal to that. Recall these are functions. The way you prove 2 functions are the same is you give them the same input and demonstrate that they always produce exactly the same output. If 2 functions always behave the same, they are the same. Right. Okay. Okay, so here we go. How do I compute this thing here? Well, notice I have a product. Products are compositions. Right? So whatever I'm going to plug in here, this V, I first plug it into T, and after that, I plug it into R plus S. So products are compositions, straight out of the definition from 2 pages back. Okay, next, what have I got here? Well, I have a sum. That plus that. And how do you compute a sum? Well, a sum acts on a given vector by adding the individual outputs. Right, so this is the definition of, a consequence of the definition of addition of linear transformations. So notice I didn't really do anything there. I just followed instructions, right? I interpreted this product per the definition. I interpreted this sum per the definition, and this is what comes out. Now we just do the same thing to this other line. And it's morally equivalent here. Again, I have a sum of 2 things. Sums are defined by adding the individual outputs. Right? This products are defined by compositions, just like in the definition a couple pages back. And lo and behold, note we get the same thing out of both of these functions. Therefore, these functions are equal, and that is exactly property 8. So, and that's the proof. It's just directly checking that it is that it behaves the way it's supposed to behave. Okay. All right. So, try to digest this proof. Make sure that you can apply the idea here, adapt it appropriately to a couple of other of these. It doesn't matter which ones, maybe this one and I don't know, that one or whatever. It doesn't, just try a couple of them, make sure that you can make it work. Okay. Couple of bits of setup. We have all of our definitions really kind of worked out at this point. Now I'm going to start building up some machinery that'll apply to to what we're actually interested in. Recall what I've claimed is that we're going to be able to prove some theorems about differential equations here. In order to be able to prove those theorems, I need to build up some machinery, and those machinery are made out of certain kinds of cogs and wheels, and I just got to define the cogs and wheels now. So step one, y'all recall this thing. This is a linear transformation. We actually we directly proved in class last time, I think it was, that this is a linear transformation. So I hope everybody remembers that one. Here's another one. Here's an unremarkable linear transformation. Given a fixed function g, this linear transformation takes as its input some function f and produces as its output g times f. So this linear transformation is what you might call the multiply by g linear transformation. If you give me a c infinity function, I give you a c infinity function. Okay. Not hard to prove that this is a linear transformation. Nice little exercise. Make sure you can do this kind of thing. I've given you a bunch of suggested exercises of this form. And again, every time you want to prove something's a linear transformation, you can just directly put a linear combination in, confirm that you get the appropriate linear combination out. Okay. All right. Okay. Now, here's a weird observation. Remember, we've looked at these differential equations here. That chapter 4. That's what chapter 4 was about. In chapter 4, we drew our attention to the left side, and we rewrote the left side as L of y. As a nice little shorthand, right? I mean, the left-hand side here is this great, big monster of terms with a ... in it, and it's clunky, right? And it's very convenient just to describe it as L of y. In other words, L says, whatever y you give me, L says do all that junk. That's what L of y is. Nice shorthand. We proved a long time ago that's a linear transformation. All right, so the observation I want to make here is that, well, in fact, this does the same thing. It's just a matter of directly confirming, but here it is. Let's walk through that. What does this term do to y? Let's think it through. We've got a product. Right? Products are defined as compositions. So we're going to take y. We're going to do whatever this says first, and whatever comes out, we're going to do this too. So namely, we're going to take y. We're going to take indifferent derivatives of it. And having taken indifferent derivatives of it, we're then going to multiply by this function called qn. And notice that produces exactly that. I mean, it's exactly the same thing. We took y, we took n derivatives, and then we multiplied by this other function qn. Right? So likewise for the rest of the terms. Right? This acts on y to produce that. Yeah, that is just observation. So here's where we're at then. L of y was how we represented this in chapter 4. We're seeing here now that this is another perfectly fine way to represent exactly the same thing. And as a result then, L can be thought of as this algebra. This L, this thing that, when we were in chapter 4, our perspective on L was, I don't want to write down all that junk, so I'm just going to call that process L. It was just a shorthand. And now we can make precise statements about how that L is actually an algebraic combination of much more fundamentally simple linear transformations. We can peer inside of L and see what's in there. L is made up in exactly this way as exactly those linear transformations. So right off the bat, this is getting interesting in the sense that, you know, we've got a new algebraic toy to play with, a new algebraic point of view on something that we've tried to understand previously. Okay, all right. Okay, now I'm going to make a notational observation. Going back up to here, I wanted to define this linear transformation. I wanted to emphasize that this is a linear transformation, so I gave it a name, a label, what it looks like. But now I want to point out that there's a much simpler notation that you can use to represent the same thing, and that is I can just, instead of saying let's apply the linear transformation that multiplies by Qn, I could just write a Qn next to it, because our standard convention is that writing Qn next to something means multiply by Qn. Right? So this is just a sort of a notational alternative. Up to now, it's been beneficial to see that as a linear transformation, and now I just want to make our notation in life a little bit simpler, so I'm just going to write it like that going forward. Okay. Alrighty. Old observation, but we already made this observation, but if you want to solve a homogeneous equation a la chapter 4, well, you want to solve L of y equals 0, the way we might say it in chapter 4. Well, L of y equals 0 means you're looking for the kernel of that linear transformation L. So just a reminder, again, we saw this last time, but the chapter 4 notion of solving is in chapter 5 the notion of finding a kernel. Okay, so we're going to move on now to considering the constant coefficient case. Remember, 4.2 is all about 4.2 and on. It's all about constant coefficients. So our L now, let me write it up here. L is now an d to the n plus etc. Plus a1 d plus a0. Okay, where these are constants. Okay. All right. So weird suggestion I'm going to make here, but I claim that. Gosh, this seems weird. L is equal to P of D. And let me take a moment before I persuade you that this is true to talk about what a crazy assertion this is to look at. Let's just sort of step back from it. L is equal to P of D. Right off the bat, here's what always bugged me the most when I was first looking at this sort of thing. P, characteristic polynomial, is a polynomial. Right? I mean, y'all remember polynomials? Algebra 2, way back when? Algebra 1 maybe? But certainly Algebra 2. And how do polynomials work? What is a polynomial? It's a function where real numbers go in and real numbers come out. That's in Algebra 2. That's a high school thing. Right? So, at no point in my high school Algebra 2 class did somebody put into this perfectly innocent polynomial a linear transformation. So can you do this? Is that legal? What does that even mean? Right? This is a creepy thought the first time you see it. Right? So it almost feels like let's evaluate a polynomial on trash can. Right? Can you do that? Can you put a trash can into a polynomial? No, of course not. That's insanity. So how does it make sense to put a differential operator, but a linear transformation into a polynomial? Is that okay? Here's why it's fine. Let's take a moment to recognize that it might have seemed a little weird the very first time you put a complex number into a polynomial, right? Can you do that? Is that okay? Well, yeah, sure. Because look, all you need to be able to, if you want to evaluate a polynomial, whatever you put in, you've got to be able to raise it to various powers. You've got to be able to multiply it by itself, in other words. You've then got to be able to multiply by real coefficients. scalars. And then you've got to be able to add the kinds of things that you produce with those operations. Can you do that with complex numbers? Sure. You can raise complex numbers to powers. Sure, you can multiply by scalars. Yeah, you can add them, these kinds of things, to each other. No problem. We had those operations, so plug them into a polynomial all you want. No issue. And we can do those things with linear transformations as well. Right? D is a linear transformation, the result of which can be plugged into this linear transformation. So you can compose this all you want. So you can raise D to whatever power you'd like. And we have formulas for how to multiply by scalars and formulas for how to do all sorts of things. So weird though it seems, this is not nonsense. This is actually a thing. You can do this. That's fine. All right, now here's what remains. I hope you'll buy my assertion that this is not garbage. Now, the second step, I have to assert to you that it actually is L, as I'm claiming it is. And that's, how do we see that? No problem. Let's write down what our characteristic polynomial is. P, I guess I'll do it here. P of lambda, remember, the way you write down P of lambda, A-N, lambda to the N, plus plus lambda 1, A1 lambda plus A0. That's what your characteristic polynomial is. And now let's plug D into that. So P of D, everywhere I see lambda, I've got to put a D. Uh-oh, what did I just do there? Cancel. I hope I didn't just... Okay, there we go. I think I just hit the wrong button there. Sorry about that. Everywhere we see lambda, we're going to put a D, and we get A-N, D to the N, plus plus A1, D, plus A0. And sure enough, P of D is L. There it is. So this is not nonsensical garbage. This is ultimately a notational observation. It's really all it is. Right? That the act of creating the characteristic polynomial by changing D's into lambdas, followed by plugging in D, namely changing lambdas back to D's, doesn't change anything. There it is. It just is what it is. All right. Okay. Nevertheless, creepy. Give yourself a little time to digest that. It's kind of weird observation. Okay. Next observation I want to make. In general, we've already made the point that multiplication is not commutative. In this case, for these linear transformations, the reason it's not commutative is kinda because of the product rule. When you take a derivative of a product rule says you get these two terms, right? Whereas if you do it in the other order, if you take the derivative first, there's no product rule. You're just taking the derivative of just f. And then if you subsequently multiply by g, okay, but there's no product rule, right? So that extra term from the product rule is why they don't commute. So the clever observation to make here is that, okay, well, yeah, but if g prime, what if g prime were 0? If g prime were 0, well, that would mean g is a constant, which it is. Right? We're looking at the constant coefficient case. So being that this is constant coefficient, those terms go away. Said differently, if you just multiply out, if you multiply by a, then take a derivative. If you, on the other hand, take a derivative and then multiply by a, you get the same thing. So neat. Really, good fortune. We had to, we had a little disappointment in multiplication wasn't commutative. But now, given that we're looking at constant coefficient, transformations, it is commutative. And this actually gives us a really nice benefit as follows. I claim that means that not only can you do a lot of algebra with linear transformations, but you can factor. And I claim that commutativity is exactly what you need to make factoring work. Let me just write out a sort of an algebraic example. Let's multiply d minus 2 times d minus 3. All right, and then we're just going to FOIL this out. So I have d squared minus 2d. Be careful with this next one. The next sort of term in the FOIL, you're going to want to say minus 3d. You've got these strong algebraic instincts from middle school or whatever that, d times 3 is 3d. You're supposed to just whip those constants out to the front because that's just what you do in high school algebra. At this point here, we don't know that works, and so I have to say minus d3. Right? And then plus 6. So can I rewrite this? Can I combine these into minus 5d? Well, what I need to be able to do there is commutativity. Right? Commutativity is exactly the tool that you need to be able to rewrite this as, what you were hoping all along, like that. Or said differently, commutativity is the tool that you need to be able to take a polynomial and factor it in all the old familiar ways. So, since we have established that, in our case of constant coefficient operators, we do have commutativity, we therefore also do have factoring. It's a nice feature to have. All right. Now, I am aware of the fact that this is pretty dry. Right? This is pretty dry stuff, but we now have some really powerful tools. It's going to turn out that we have all the powerful tools that we need at this point to make some amazing insights about differential equations that we just could not have dreamed of doing back in Chapter 4. So, and I know we're short on time, but I do want to show you at least one of them. The first one I want to start with is looking at homogeneous differential equations. The very first thing we did with homogeneous differential equations, such as this, is we started writing down solutions. And I did something highly suspicious. First cat out of the bag, when we started doing this in Chapter 4, we wrote down our equations. And I just sort of out of thin air said, I wonder if exponentials work. And they worked, and they were exactly the solution that led to all the other solutions, and it wasn't that nice. Wasn't that good fortune, right? But also, isn't that highly suspicious, right? I mean, isn't it unsatisfying that I just came to you with the solution? I gave you no suggestion of what my motivation was. You should be thinking, you could very reasonably have been thinking, but where did you come up with that? Right? And where did I come up with it? Well, somebody showed me. Where did he come up with that? Well, somebody showed him. Right? So ultimately, what's the motivation for trying exponentials? Why should we have considered even the possibility of trying exponentials? And I'd like to show you a motivation for that. Keep in mind, we just showed that L is not only made up of an algebra of linear transformations, but that it factors. Furthermore, not only does it factor, but these factors are commutative, and so we can move these factors around however we like, which is weird, but true. And I would like to move those factors around as follows. I'm going to take arbitrarily any one of those factors, move it over to the right, take everything else, lump that over there on the left. I don't really care how you lump it over there, just kind of throw everything else over to the left. Okay. And then I want to look at this resulting differential equation, and let's strategize. And this is a really simple, ultimately, point. Nth order differential equation. Haven't the foggiest clue of how to make this whole thing turn to zero in general, but check this out. If I can come up with some way, wouldn't it seem plausible to speculate hey, if I can find some way to make this 0, we win. Right? Now, this is not a leap of faith. If I can find some y that when you apply d minus r gives you 0, if you can make this purple thing 0, game over. We win. Who really cares what this Q linear transformation does? Right? So my goal of finding a solution simply comes down to how can I solve this differential equation? Which, if you write it out, is exactly a natural growth equation, which we already know the solutions to. So, if you had not had in Chapter 4 this wonderfully convenient, isn't that good fortune, guess of trying exponentials, you could just as well argue with no instincts at all that using this algebra of linear transformations, we can motivate the idea that we should be looking at solutions to the natural growth equation. If we can solve the natural growth equation, which of course we can, then check it out, that's clearly going to work, and therefore we found a solution. So I think that's very satisfying that we now have a motivation for that which I previously just pulled out of thin air. And we'll see much more good stuff after spring break. Y'all have a great break.